Good day to everyone. Today I'm presenting on the topic, compressive strength and pore structure studies of clay-fired waste powdered clay brick as a supplementary cementitious material. My name is called Mark Bediako, and I'm from Ghana, which is located in West Africa. I work with the Building and Road Research Institute. So with the introduction, we all know that post-industrial revolution has caused depletion of natural resources. Our timber is being depleted. The building industry is also generating to the depletion of resources such as aggregates, water, and wood. The same thing is happening in the cement industry, which is depleting finite limestone resources. And it had been indicated that 1 ton of cement consumes approximately 1.5 tons of natural resources. Now, all cement industry also contributes to the generation of carbon dioxide emissions in the atmosphere. So in a way of reducing these resource depletions, there are proposed sustainable strategies. And some of these strategies that have been proposed include a criteria to select our material for construction very well, where the concentration should be on low environmental impact materials. And then we can also look into the optimization of cement-based products, where we use what we call supplementary cementitious materials. So the motivation of this study is to optimize cement utilization in mortar and concrete. But if I am to do this work very well, I would like to valorize waste brick powder and use it as a pozzolan. And we know that the pozzolan utilization when using mortar and concrete can be a way of reducing carbon dioxide emission in cement usage. So about the clamp firing of clay brick, this is how the clamp fired bricks are prepared. You know, we have the down part and the fire boxes that is usually filled with waste wood or timber. And then we ignite it by firing it and then fire the bricks. But when all these things are done, the clamp firing technology generates between 10 to 15% of waste. And this waste has an improper way of disposal. Sometimes they go into landfilling, and when you go to places that they do this kind of firing, you see this waste being left on arable lands. And so what we're saying is that before you can do all these things, we need to pyroprocess or heat treat clay. And we know that heat treated clays can be used as a possible supplementary cementitious materials. So the objective of the study is to utilize the waste brick as a supplementary cementitious material. But before I can do that, I have to look at the strength activity index of the waste brick. Then I will also zoom into the transport property of the material that will be used to produce mortar. Then I will look at the microstructure property using nuclear magnetic resonance. So the materials that were used for the study, I have Portland cement, waste clay brick that was milled, having a size less than 75 microns, and I have pit sand. Then we have a high range water reducer in the form of sulfonated naphthalene formaldehyde. So for the method, we prepared our mortar by using the ASTM C109 method, which prescribes a way of preparing mortar. And then we determine our flow of the mortar using the ASTM C1437. These mortars were cured at 3, 7, and 28 days in lime saturated water solution. For the sorptivity test, the method was in accordance with the ASTM-C 1585. And then we performed the NMR using the solid state aluminum and silicon NMR method. So the results and discussion, these are the key points. Number one, we realized that 30% of the waste clay bricks showed high early and late strength development. So if we come to this graph, this is the control graph, and now 3 and 7 days at 30% attain higher strength, which is the early strength, than the control. And then at 28 days, which is the late strength, it was also higher than the control. Comparing it to the other percentages, they were all higher than 10, 20, and 40%. So at 3 and 7 days, it was 11% and 9% higher than the control. Whereas at 28 days, the 30% waste replacement was 9% higher than the control mortar, which is this one. So with the sorptivity test, we look at the capillary action. So at the primary sorptivity, these are what we are having. So for the control, this is the control line, and then the one that is containing the waste clay brick. Of course, we can see that that one was very lower. So we're having a gradient of 0.0055 compared to that of 0.0299. So which means that, the one containing the waste clay brick has the ability to resist the ingress of harmful ions. It was the same like as the secondary sorptivity. We have the one with the waste clay brick at 0.0022 compared to this one, which was 0.0083. So it can be concluded that this is much lower than the control. So we did the microstructural analysis using the NMR, AL, and SI NMR. But for the purpose of the time and the presentation, I'm just limiting myself to the SI NMR. So this is the control. The point of interest is at -103. So you see that there's nothing happening here, but when you come here, we see that there is a little bit of a peak. Now this peak is very significant to the study of polymerization. So we can see and we can conclude that what is happening here means that calcium silicate hydrates are being formed. And that is the more reason why we had the 30% mix having higher strength than the control. So in conclusion, what we are saying that the clay brick powder mortar mixture that contain 30% of the material attain the maximum strength at 3, 7, and 28 days. The strength gain over the control mortar at 3, 7, and 28 days were 11%, and 9% respectively. The water sorptivity values of the PWCB cement mortar were lower than the control mortar. The formation of stable monosulfates, AFM phases, an increased amount of calcium silicate hydrates in the blended cement paste than the unblended one at 28 days accounted for the high strength and lower sorptivity values than the control. So thank you very much. And I'm ready to answer any question. Thank you.